In the last class, we looked at signaling inside a neuron, and after considering all the biological aspects, we have come up with a very simple picture of a neuron. That is, a neuron basically can be in two states: a resting state where the voltage is at a baseline value, and the accelerated state where the voltage can go up and repeatedly show this spiking activity. Right, and then a neuron can receive inputs from many other neurons through two different kinds of synapses. Some are excitatory, some are inhibitory. And excitatory synapses tend to increase the voltage of the neuron, and inhibitory ones tend to decrease the voltage. And the net influence of all these inputs, excitatory, inhibitory, is such that it increases the voltage of the neuron above some threshold. Then the neuron goes from resting state to excited state and fires action potentials. Then the whole cycle continues because these action potentials are then communicated to other neurons and so on and so forth. So this kind of a neuron, a biological neuron, which is what we have arrived at until now, can be described mathematically using some very simple equations. And that's what these two guys have done way back in the early 1940s in University of Chicago. So Warren McCullough was a physiologist, and Walter Pitts was a mathematician, his postdoc. And these two people have come together and formulated this very simple mathematical model of the neuron that you have seen just until now. So in this model, a neuron gets inputs from many other neurons. The inputs are x1, x2, xi, and xn. And these are passed through certain weightages, w1, w2, wi, wn. The weightages represent the synaptic strength, because we said synapse can be strong or weak, can be positive or negative. So that property of the synapse is represented by the scalar value, the weight. And the sum total of all these inputs weighted by the weights is, if it is greater than some threshold, the neuron fires, that is output y then is 1. Otherwise, output y is 0. So here for simplicity, we take that the baseline value of the neuron is not minus 70 millivolts, but it's just 0 as convention. Because we say that the neuron here in this case has just two states, the resting state and the excited state. So resting state has a value of 0 and excited state has a value of 1. It's a very simple neuron model. But we will see that this is good enough to explain a lot of interesting phenomena about brain, and both in terms of neural activity and in terms of behavior, right, the kind of phenomena that you see in psychology. So for this to happen, you need to use a nonlinear function, because for a whole range of inputs, the output y is either 1 or 0. So that's only possible if g is some kind of a threshold function, because if the total input sigma wxi, if it's greater than b, right, then y is 1, otherwise y is 0. So g is doing some kind of a thresholding of this summation sigma wxi using the threshold value b. So it's definitely not a linear function, and you can easily argue and show that g is basically the step function, right, which is given by the function shown in the bottom of the slide. So g of h is equal to 1 for h greater than or equal to 0, otherwise g of h is 0. So this is the step function. So this is quite a simple expression for a neuron, which we thought is likely to be very complicated. And starting with that kind of a neuron model, McCullough and Pitts have shown that this neuron model can be made to represent logic gates. Because if you think about it, 1943 was a time when the World War was going on, the Second World War. And so people are using large-scale computers for war applications. They're using it to crack, the secret codes that were used by the opponents, by the enemy. And they're also using to calculate missile trajectories, apparently. Right? I don't know what kind of missiles were there in use in the World War. So the computer was being used for kind of big aims, right? So the thing is, so it is very natural to think that anything that is intelligent, logical, capable of superior mental function must be working like a computer. It's a very logical assumption. So and also they have started with a neuron model, not some Boolean logic gate or something. And then they were able to show that using such a model, you can implement the logic gates very simply like this. So for example, if you want to implement the OR gate, right, the OR gate truth table is given here at the right top of this slide. That since the two inputs x1 and x2, if both inputs are zeros, output is 0. If it is 0 or 1, output is 1. If it is 1 and 0, output is 0, output is 1 again. Only when both inputs are 1s, the output is 1. So, okay, so to get that, if you look at the expression on the left side, please mute yourself, otherwise you'll get this echo, which can be very annoying to everybody. So, so on the left side, the expression that you see is g of x1 plus x2 minus 0.5. Okay, so you can see that when x1 and x2 both are zeros, the argument is negative, so output is 0. Even if one of the inputs is 1, right, the argument is positive, so the output is positive because this g is interpolation. Yeah, so like that you can construct the AND gate, and to get the NOT gate, you basically g of minus x plus 0.5. So when x is 0, the output is 1, and x is 1, output is 0. Okay, so it's very easy to construct logic gates using this neuron model. And you can construct Boolean networks out of such neurons. Now, since brain is a network of neurons, you can implement Boolean circuits using neurons, which means that the next conclusion is that brain is a logic unit. So this was what they concluded, and it was a very influential line of thought, and because that has stayed with people for more than 20 years, right? And so it was very natural to think of the brain as some kind of a computer, because like I was saying, this is the ENIAC computer located at the University of Pennsylvania, right? This is the computer which was used for war applications. And, it was filling a huge, very huge building, right? And it was quite imposing. So it was clear that the power of computing, power of a computer, was very visible in those days. It's in the air. So therefore, it is natural to think that anything that is intelligent has to work like a computer. So that's why they did that. But actually, if you think about it, there are a lot of differences, fundamental differences between the computer and the brain, right? And they're not very similar at all. So let us look at some differences. So brain is a soft organic tissue. It's a 3D volume, right, of a tissue. Whereas a computer, which is made up of the circuit boards, is primarily like inorganic and 2D sheets of matter. The 3D part is somewhat weak. Then if you look at signals, again, there's fundamental difference, because in the computer, if you just put a galvanometer on any of the buses and then just measure the voltage variation, it looks something like what you see on the right side, that it's a digital signal, just going from a max value and a min value. So it could be from +5 to -5 or something like that. Whereas in the brain, if you look at the activity of individual neurons, it will be quite complicated. What is common to all of them is the sharp voltage spikes called action potentials. But otherwise, the spike pattern can have immense variation. So, for example, on the left, you see all sorts of about 20 different spike patterns. There are more, right? And then there is also on the computer side, although there's so many signals, they all are driven by a common clock, a centralized clock, right? So all the signals ride over a certain like a baseline clock at the same frequency. Whereas in the brain, there is no such centralized clock, because all neurons fire at their own frequencies. In fact, a given neuron can fire over a range of frequencies, and at a given time, it can fire at different frequencies. Even at single neuron, there is not a fixed frequency. Okay, so whole brain level, definitely it's not fixed frequency. In fact, you might have heard of brain waves, where the whole spectrum of signals in the brain goes anywhere between very low frequencies like 0.001 kind of thing, hertz, to a few hundred hertz. So it's a fairly wide range of frequencies. The only major difference is that in the computer, the frequencies are, at least particularly now, the frequencies are very high. We're talking about gigahertz and all that, but in the brain, they're very slow. The highest frequency is like a few hundred hertz. So that is there. But brain makes up for that low clock speed by using a large number of processors. because brain has 100 billion units. So if you think of each of them as a processor, that's a very large number. Nothing in the computing world can come anywhere close to that. So that is another thing. Then another important difference is that there is one of fault tolerance. A computer or a digital system is a very delicately designed, precisely arranged kind of piece of matter. Any small distortion or error in this design, in this composition, can give rise to kind of very bad output. If you take, for example, a CD and scratch on it with a with some metal rod or with a nail or something, right? You'll see huge problems in whatever is output. If you're playing a song, you'll see lots of noise in it and so on, right? And extreme case of whereas with the brain, it's very fault tolerant. An extreme and dramatic example of brain's fault tolerance was the incident which is much cited in neuroscience history literature. So there was this guy called Phineas Gage. He was a railroad construction worker working in the US in the late 19th century. So his job is to kind of pack ammunition inside the ground and basically put bombs and break ground. Okay, there's very hard ground with a lot of rock and all that. You need to break it using bombs, and then you can soften it and you can lay down the railroads. So he was doing that once, and accidentally the bomb went off even while he was doing it. So the crowbar with which he was packing the bomb deep inside a hole, right? It went through his head, went through his face, and came out of the head and just remained stuck there halfway in his head. It was a pretty gory accident. So they carried him to a nearby hospital, and with some really difficult surgery, they cut that crowbar and removed it and so on. So normally you would think the guy would die in a few minutes, but actually he didn't die. He survived about the journey from the accident site to the hospital and also the surgery. He survived the whole surgery, but he had serious personality changes, which is a different matter. So the point is, brain is so fault tolerant, it's so forgiving of errors. Whereas imagine what happens if you drive a crowbar through the chassis of your mainframe on your CPU sitting on your desk or on your desk. Right, I mean that's the end of story. Even if you shake it a little bit, right, it stops working. So actually, even if there is because if you have a lot of dust collecting, right, at least these days there's a lot of computer labs have AC. But when I joined the institute, there was no AC, and so computer used to stop working just because there is no AC and because there's a lot of dust and it picks up, develops loose contact. So it is so sensitive, right? Whereas brain is very fault tolerant. Then brain learns by error feedback. How do you, for example, how do you learn how to do a tennis serve, a perfect serve, right? And the coach doesn't tell you, okay, you bend your racket by such and such angle, theta and alpha, and then exactly follow this trajectory, and it doesn't work that way, right? So you have to serve, and he gives only some kind of a very general specifications, and you have to serve and look at the error. Is the ball falling exactly in the opposite court, or is it kind of getting stuck in some tree, or right? Based on that error feedback, you gradually adjust your serve and learn how to serve, right? Whereas if you look at a computer, even a robot which is designed like a computer and not some kind of neuromorphic modern robots, it's all pre-programmed. So you have to program it, and then you just follow the program. So that these differences between a computer and then the brain started becoming obvious, right, over the following decades. Then people started thinking in new directions to understand how a computer works. So they understood that neurons cannot be behaving like logic gates, and computer is not a Boolean circuit because we have all these fundamental problems. It must be working very differently. It's still made up of neurons, obviously, but these neurons are doing something else and not implementing logic gates. So that thinking had led to the creation of something called a perceptron, which was proposed by Frank Rosenblatt in 1957, but they became popular in the 60s. So these neurons are small networks made up of the same McCullough and Pitts neuron models. they could be trained to recognize some visual pattern. Okay, so the point here is they could be trained, whereas in the previous version, the Multilayer conception, they had to program, the weights had to be preset, by some kind of a mathematical analysis. So here, whereas in Rosenblatt's machine, the weights are automatically trained. You don't have to preset them. So he called it the perceptron, so that it will have a kind of nice ring to it, because it's a perceiving machine. Right? So how does the perceptron work? So there is a neuron or a small network of neurons, and it's supposed, let us say, classify some patterns. Let's say it's supposed to read alphabet, ABCD. We present a pattern and look at the output. If the output is the correct output, that is, you give letter A, and output indicates letter A, then that's correct and no change. Move on to the next letter, and then it's present B. And instead of saying B, if the network says it is C, then there is an error. So that error is fed back and to the network, and network corrects itself. All the weights in the network are corrected slightly, right? And in such a way, next time when you present the same pattern B, the network has a better chance of saying B and not C. So it learns to correct itself by error feedback. So that is called the perceptron learning rule. And Frank Rosenblatt proposed one such algorithm. Yeah, so there's some algorithm, and I'm not going to spend any time on the mathematical aspects. Right. So basically, what is happening here is the way this neuron is working is, like I said, for a given input, the output can be either 1 or 0. So if let us say you're looking at two-dimensional inputs, the input has two components, x1 and x2. So for that means inputs are coming from a plane. So for any point on the plane, the output y is either 1 or 0. So how do these regions look? So if you look at the entire region where the output of the neuron is 1, y equal to 1, entire region where the output of the neuron y is 0, how do these regions look? And how does the border between these two regions look? So if you to answer that question, you just look at when do you get the border? Okay, so that is when the argument is positive, you have y equal to 1. When the argument is negative, you have y equal to 0. So when do you have the border? When the argument is 0, right? So that is when sigma wi xi minus b is equal to 0. So that happens to be a straight line, right? So it's a very simple border. So basically, the neuron is dividing the entire input plane into two halves, two infinite halves. And so on the one half output is 1, other half output is 0. So now you can, so earlier we have shown how you can just preset the weights and make the neuron behave like a logic gate. But now with perceptron learning rule, you can train the weights and make the neuron behave like any of the logic gates. So here we have taken the data from the OR gate, so that is only when it is 0, 0, the output is 0. I don't know if you can see there are this green circle here, right, indicates output of 0, and the crosses, blue crosses, indicate output of 1. So just indicate that there are two classes in this data set. So initially the decision boundary is here, which is wrong, right, because it's putting all the 4 patterns in one class. So when you present the first input, it will give a wrong, it will give a wrong answer. When you give second input, it gives correct answer. Third also correct answer. Fourth also correct answer. So out of 4 patterns, it's giving 75% correct, right? So then you train it again, update the weights. When you do that, now the weights have changed. So the decision boundary has changed. And now you see that the pattern for which it was making a mistake earlier for 0, 0, it's now giving correct response. Correct response for 0, 1, correct for 1, 0, correct for 1, 1. So it's able to learn the correct responses for all the 4 patterns, 7%. So this gives a flavor of how this kind of a neuron can learn to classify. It's a very simple example also. So, but thing is, very soon it became clear that a perceptron can work only when the classes, the data correspond to the two classes, are linearly separable. That means there must be a straight line which can separate these two classes. Or in n dimension, there must be a hyperplane which separates these two classes. Otherwise, it won't be able to learn. So that was a big drawback of perceptrons, and that there has to be a straight line or a hyperplane which can separate the data corresponding to the two classes. So on the left, for example, you are seeing an example where you can separate the two classes using a straight line. Whereas on the right, you see that the data cannot be separated. That is, the greens form one class and the blues form another class. So on the right side, the blue circles and the green pluses, right, cannot be separated by drawing a line in any way you want. Okay, so if you train the perceptron on the data on the right side, it won't be able to learn it. It will keep on searching for the correct answer. So similarly, if you take one of these logic gates, so the three fundamental logic gates are AND, OR, and NOT. But if you take another logic gate like the XOR function or XOR gate, right, where the truth table is given on the right side top. So 0, 0 is 0, 0, 1 is 1, 1, 1 is 0, and 1, 0 is 1. This is the truth table. So therefore, if you divide the 4 data points into 2 classes, right? One class, each class is occupies opposite corners of the square, right? So no matter how you draw the line, you won't be able to separate the two classes. So therefore, if you train the perceptron on this kind of a data, it won't be able to learn. Right. So no matter what you do, the error won't go less than some value. So that became very clear as a very deep drawback of perceptron. So Minsky and Papert, two major figures at that time, and who were actually one of the key figures in the artificial intelligence revolution, which was just emerging in the 60s. they incidentally wrote a book on perceptrons. And in that book, they have given a really scathing criticism of the perceptron model. So this is what they said. The quotation is given below. The perceptron has shown itself worthy of study despite and even because of its severe limitations. The idea is like when something has some flaws, you feel like studying it even more, just to make sure that what are the borders of that those drawbacks. It has many features to attract attention. Its linearity, its intriguing learning theorem, its clear paradigmatic simplicity as a kind of parallel computation. There is no reason to suppose that any of these virtues carry over to the many-layered version. Nevertheless, we consider it an important research problem to elucidate or reject our intuitive judgment that the extension to multi-layer systems is sterile. So in a perceptron, there are just two layers. That is a layer of neurons and the inputs, right? Whereas you can, in principle, construct multi-layer versions of the network. That is, you can add more layers to it. That is, the output of vast layer of neurons will become input to the next layer, and so on and so forth. You can add any number of layers in principle. Only thing is, coming up with a learning algorithm for such networks will be much harder, because perceptron is very easy. It's a very simple model. So these guys were debating in that book whether it's worthwhile to study multi-layer versions of a perceptron, or is it just a waste of time? They decided it's a waste of time, and since they are big shots in the field, I don't know how they are big shots because it was such a poor judgment, right? People didn't dare to study perceptrons in greater depth for a long time. So this was book came in the 60s, and whole of 70s there was not much work. Not much work was done. Actually, there's one interesting study by a guy called Paul Verbos who wrote a thesis in MIT, but nobody paid any attention to it. Okay, but in the 80s, again, things suddenly started picking up, and people started studying the multi-layered version of the perceptron which has more layers. And since then, things start picking up in a big way. So what is this multi-layered perceptron? So in a perceptron, you just have two layers, like I said. There's input layer, right, and then there's output layer. In output layer, some of the examples we have seen has just one neuron, but you can have any number of neurons in that layer. So it has basically two layers. Whereas in a multi-layer perceptron, you can have any number of layers, right? And just like in a perceptron, there's an input layer and an output layer. Between these two layers, you can have any number of layers. These intermediate layers are called hidden layers. It can have one or more hidden layers. And such a network has kind of, you can think of it as an input-output machine. That is, it takes an input and produces an output. It can map an input onto some output. Now, this mapping between input and output, between X and Y, is parameterized by a bunch of weights, because inside the network you have lots of neurons and lots of weights. And the weights have unknown values initially. So only by training you set these weights. So by training these weights, you can make the relationship X and Y whatever you want, in practically speaking. Right? So which is like a nice black box which can learn anything. So people began to think of the multilayer perceptron as a regression tool, as a curve fitting system, as an algorithm for curve fitting. Right? Because in curve fitting, what do? You have two variables which you have to, for which you have to fit a curve, right? X and Y, and the data is given to you in the form of some kind of XY points, Xi and Yi, and you have to fit a curve through them, right? You formulate some kind of a error, the output error between the actual value Yi and your estimate, some Yi hat, let us say. So Yi minus Yi hat whole square must be minimum, right? And for that to happen, the curve will have some parameters, some ABCD or something like that. So what should be the curve parameters so that the fit and the data match very well? So this is the problem of regression. So people started, began to understand that MLP is a regression tool. Well, then it's a very complicated regression tool. It can map not just a single X and a single Y, but lots of X's and lots of Y's simultaneously using a highly nonlinear function, right? So MLP began to be called a universal approximator, because mathematicians have analyzed these kinds of networks and found that an MLP with a single hidden layer can approximate any continuous input-output function with arbitrary accuracy. Whatever accuracy you want, it will give you that. Or a finite input domain, as long as your input domain is finite, right? Given enough number of neurons in the hidden layer. So if you have enough number of neurons in the hidden layer, this kind of a network can learn anything practically. Okay, so that was very interesting result. And since it has the property, MLP is called a universal approximator. It can approximate any unknown function. Okay, and so the degree of fit determines the accuracy. That is, if the fit is linear, it can be a very coarse fit. If the fit is, for example, for this data, what you see in the figure, right? If fit is a parabola, quadratic, right, it will be slightly better. If the fit is cubic, so because this data seems to have like tool wiggles, therefore you need at least a cubic polynomial to fit it. So basically what we are doing here is you're adding more terms to the fit, and as you add more and more terms, it's getting better and better. So similarly, in the case of a neural network or a multilayer perceptron, you add more neurons or more layers and it gets better and better. It can learn your complicated function better and better. So you can show that so MLP is a lot better than a perceptron. So what is a problem that a perceptron cannot learn, right? Could not have learned, and MLP can learn that, can easily be demonstrated. So, for example, if you take the same XOR problem, which a perceptron cannot learn, you can very easily show that MLP can learn that. I mean, it's just a simple. So the network again works like before. You think of the network as having input and output. So you present an input and look at the output. If the output is correct, then there is no change to the network. If the output is wrong, then you compare the output with the target output. So what's the desired output? And take the error vector, the difference between the target and the actual, and feed it back into the network. And there's an algorithm which will let you change all the weights in such a way that next time when you present the same input, the output Y will be closer to your target output. So there's a very elegant algorithm which has been discovered by several groups almost simultaneously within a small short span of about 2-3 years in the middle of mid 80s. So it became clear that there is a fundamental difference between how neural networks approach problem solving, and which is quite different from traditional computer science type problem solving. The traditional approach is what is called algorithmic approach, right? And that is you study and find out the steps to produce a final output. Okay, so in an algorithm, basically you start with a bunch of numbers, right? And then perform some operations and end up with a bunch of other numbers, right? And whereas in a neural network, and also you need to know a priori what is the procedure by which you transform those numbers into those final numbers. Whereas in neural network, you don't have to know the procedure. You just have to have lots of solved examples, with lots of sample data, and the network will learn the function by itself. You know how to do that. So this is a new approach to problem solving, and also it turns out that it's closer to how we learn things. You know, suppose you are teaching a small child how to read alphabets. You show the child, say, picture of letter A or something, and then you ask the kid to say A. If the kid says A, then you say that's very good, and you give a pat on the back or a lollipop and things like that. If the kid says B, then you give a little whack and say, no, don't say B, it is A. And so the drama continues. So, so that is the neural network approach, and kind of closer to how we learn. Whereas with a network, with a computer, you have to pre-program it and have to reduce the problem to a bunch of rules, right? A bunch of steps, and you have to execute those steps in that order. So this also highlights the difference between the AI approach, the traditional AI approach, and neural network approach. So in the 60s, AI was just picking up, and so there was a lot of hope and expectation about this growing field, this emerging field. And people thought that even the most complex, intelligent, and creative function of the brain can be reduced to a bunch of rules, a bunch of steps. And if you crack the steps, you understood the secret of intelligence. Whereas in neural network philosophy, right, it's not you cannot reduce intelligence to a bunch of rules. It is something that emerges by interaction of the brain with the world. Right, since the world is complex, and interaction can result in some kind of a very interesting intelligent behavior. So there was this rivalry between the two, and initially AI seemed to be winning the battle. But in the 80s, suddenly when all this the backprop algorithm for training an MLP, right, it was discovered, and they began to show that this kind of networks can learn a wide variety of problems, right, both in psychology and on one side, and in artificial engineering domains on the other. So it seemed to be winning the battle. And in the late 90s, the neural network fever seemed to be going down again, because there seemed to be some kind of saturation. It was clear that you cannot do things beyond a point, right? But in the 2000s, at least, that is like first decade of the new millennium, around 2005, 2006, this Hinton and his colleagues, they have, Jeff Hinton and colleagues, they have actually rediscovered that an MLP with lots of hidden layers, right, can solve very hard problems. Thing is, we knew that all along. I mean, that neural network with lots of hidden layers can perform interesting functions. But people in the early days, in the 80s and early 90s, people were mostly focusing on neural networks with single hidden layer, because even the theoretical results were mostly for a single hidden layer. And also because of computing restrictions and limitations, people were mostly training single hidden layer networks. But the mathematical theory itself was applicable to any network of any number of hidden layers. But since in the 2000 decade, right, decade of the 2000s, the computing facilities also have improved a lot, and people began to train larger computers, and were able to show that things that could not be done by former and simpler, smaller neural networks, they could be done by these larger neural networks, which they just kind of rebranded as deep networks. So again, the neural network seemed to have won the battle, and beat AI. But then AI has done something brilliant, highly political. Right? AI said, even this is AI. Whatever these guys are claiming in the name of deep networks, is actually a part of AI. It's a chapter in AI. It's all AI is everything. So then there's no more battle, because if you say that your enemy is a part of your own kingdom, right? Then there's no more battle. Okay, so that's how the war between neural networks and AI kind of got resolved in a weird way. So so people all these guys have discovered an algorithm called the backprop algorithm. Right, Paul Verbos in the 70s in his PhD thesis, which was not noticed until much later. Then Rumelhart, McClelland, Williams in 86, and Parker 85, Lacoon 85. So all about this span of about 2 years. if you ignore Paul Verbose, have discovered pretty much same algorithm. So the way it works is, you take a network with lots of hidden layers, you present the input X and get the output Y, right? And then compare your actual output of the network with the desired output T, and you get the error vector delta. Then there is a way of back propagating this error vector, down the layers of the network. And once you back propagate, you can, update all the weights using a very simple rule. So I'm not going to the mathematical details, but I just want to highlight the principles in this course. So if you train a network on XOR problem, MLP with 2 hidden layers. So look at this video. You see the XOR problem on the right side. You have opposite clusters of points belonging to the same class. It was able to learn it very quickly. Okay, so there is no mystery, right? Now let us take a slightly harder problem, what is called the double spiral problem. So you see that the orange dots in this picture, they all form one class, and the blue dots form another class. So it's a very hard problem to separate these two. So let us take an MLP with 1 hidden layer, and because your theorem says that 1 hidden layer MLP is good enough, right? Yes, so let us see what happens. So the yellow and blue regions are the decision regions. So that's what the network is able to divide the space into those 2 regions, right? So it didn't work that well. So in practice, it didn't work that well. So then they've chosen 3 hidden layers, right? Still crunching, still trying to learn and resolve the 2 regions, which is very hard to distinguish. Then they went for 5 hidden layers. Still is struggling, but you see that it seems to be able to make it this time. Yeah, right. It's got a lot of patches, right? Yeah, so the 3 patches now they're all merging. See, all the yellows have formed one continuous patch, all the blues have formed one continuous patch. It's able to successfully divide the whole input plane into 2 regions, where each part is spiraling around the other. So the thing is, you can see that in the simple example of how a multi-layer network with more layers can learn more complex functions. Okay, so the merits of MLP, it's a very general solution to a large class of problems. If the problem involves some kind of a mapping between some input and output, right? And if you have lots of sample data, you can just train the network on this kind of sample data and it can learn it, provided the network is complex enough. That is, does it have enough number of hidden layers and enough number of hidden neurons in those layers? Okay, so the thing is, how many hidden layers are necessary? How many hidden neurons are necessary? There's no simple answer to that. Because there are some theoretical estimates, but they are quite useless in practice. So you can only do it by trial and error. Right, and also the algorithm is applicable to arbitrary number of layers. You can even have partial connectivity. You can have inputs presented not only at the so-called input layer, but you can also present inputs at some hidden layers. So all sorts of architectures can be supported by the MLP, the backprop algorithm. The only condition is that there should not be any loops in the network, because each weight has a directionality. And the weight goes from one neuron to another, not in the backward direction. So if you traverse the network, sorry, by following the weights, you should not be able to come back to where you started. So that means there's no loops in the network. That's the only condition we need for the network. If the network satisfies that condition, you can apply the backprop algorithm to train that kind of network. So training is local both in space and time. That is, to train a given weight, all that I need is information coming from the 2 ends of that weight. So if let us say if I have a network with 10 hidden layers, if I'm training a weight in the first hidden layer, I don't need any information about what's happening in the network, in the 7th hidden layer. So all that I need is at this connection, what is activity at the input end of the connection and output end. So which is a very nice property, because that's how you would imagine the real brain would be working, right? Because in a given synapse, if I have to change something, all that the synapse has access to is information from the presynaptic terminal and the postsynaptic terminal. Something happening many synapses away from that synapse, so it won't be able to know. So the learning algorithm should have that property, that basic property of locality, right, both in space and time. So similarly, in synapse cannot be modified by some event that has taken place, 10 minutes away ago, a long time ago, because how does a neuron remember information about events that happened long ago? Okay, so everything has to be local, both in space and time. So that property is there with this backprop or backpropagation algorithm. So this network, this class of models, they were successfully applied to a wide variety of phenomena in psychology and neuroscience. So that was a big hit, and people that has led to what is called the connectionist evolution in the 80s. So where people found that networks with these kinds of connections, lots of connections, large networks, can be trained, can learn large number of wide variety of problems. And one more thing is the information is all stored in the network in the form of connection strings. So it's all in the connections. It's not in the neurons per se. It's in the connections. So the importance of connection had become more obvious with all these developments, and that is the underlying philosophy of connectionism. The idea that realization that connections are more important. And demerits is that the neuron model is too simple. Real neurons are a lot more complicated. I mean, we have seen a little bit of how a real neuron works, and it is actually a lot more complicated. So whereas the MLP neuron is quite simple because it's just the McClellan bits neuron model. And the requirement of teaching signal, that is, so very often what happens is when a given input, the target output may not be available, right? For example, if I have to learn again a tennis serve, there's nobody to come and tell me that you have to move your hand exactly according to this trajectory and these coordinates to make a perfect serve for a given ball, right? You have to actually move your hand like proactively, and based on some very generic feedback, is it good or bad or something like that, you can learn. So a very detailed teaching signal, which is what Backprop is based on, that is not biologically realistic. That kind of thing doesn't occur in real nature. Okay, so that's also a slightly artificial aspect of the Backprop algorithm. And the algorithm itself is biologically unfeasible because for this to happen, mathematically it is elegant and all that. But biologically speaking, when you compare your network output with some target output or desired output, you get this error signal. And that error signal is backpropagated from the output all the way to the input. So let us say there are 20 hidden layers. This error signal has to be propagated backwards from the output all the way to the first hidden layer. And how is it going to happen? It's not going to happen because the forward propagation of signal from one neuron to another, jumping many synapses, that is possible. In the real brain, you see that, right? Whereas the back propagation of error, jumping over many layers, and that is not likely to happen in the real brain. So that is slightly biologically infeasible. So notwithstanding all these demerits and all that, it's a very good model for starters because it helps people to understand a lot about how things might be working in the brain. So what we'll do, in fact, I had another PPT on applications of Backprop, but I'll skip that. What I'll do in next class is I'll straight away go to organization of the brain, right? So let us take this kind of a feed-forward architecture, just a network like this. Okay, so a network with lots of hidden layers. Let us take that as a toy model of the brain, right? And now let us start interpreting brain's anatomy in terms of such a feed-forward network, because in the feed-forward network you have input layer, output layer, and lots of layers in between. In the brain too, you can think of the brain as a big feed-forward network, where input is a sensory input, output is a motor output, right? So sensory input could be vision, touch, hearing, and all those things. Motor output could be movements of your hands and legs and eyes and all that, or your movements of your speech apparatus, your speech production, things like that. So it's just you can think of brain as a first cut, as a zeroth order approximation. You can think of the brain as an input-output system. It takes sensory input from the world, produces motor output, right, and then acts on the world back. So we'll start with that kind of a simplistic story and then interpret brain's anatomy, right, and try to make sense out of it. Why is it like that? Because if you look at it like that, a lot of anatomy makes very simple sense. If you just start mugging up the anatomy, it looks all very complicated. But if you look at it with the background of a simple deep network, it looks very logical why it is like that. Okay, so we'll begin doing that in the next class, and we'll try to cover the whole topic of organization of the nervous system, like over a couple of classes. So thank you. And by the way, when is the next exam, Sundari? Any